This is 4.1, vectors in R to the power n or Rn, second, third, and so on. Just a basic introduction to vectors, which is you're all familiar with from 250A. So I'm not going to be writing much here. I want to make the video as short as possible. This is how we add vectors, which is called the parallelogram law of vector addition. As you could see, there is nothing much here, and as I say, like it's just introduction. Just bear with me and we'll answer any questions in the class as needed. X plus y equals y plus x. Everybody knows that when we add, doesn't make any difference. You could use the commutative property. You could use the distributive property. You could add a zero vector, and that's going to keep you where you start with. That's called the zero vector. In the book, it's kind of like bold letter right here. So this is not a number zero. It's a vector x plus a vector 0 value, like 0i plus 0j equals the same vector x. As you can see, it's a different font. Those are vectors. You also have an additive inverse. So if this is 5i plus 2j, this will be minus 5i minus 2j, which is going to take you to 0i plus 0j. So that's the front page. I have divided them into 6 pages, as you can see, just to give you an idea. This is called the scalar multiplication of any vector x by k as a scalar k. You could start with x. If you multiply it by something more than 0, greater than 0, it looks like this one is twice, maybe. So if you multiply x by 2, it's going to keep the same direction, same angle, and it's going to extend it by a factor of 2. Same thing happens if you multiply by negative 2, if this is twice as much. So basically we're looking at vectors and scalars as in real numbers. In short, we call them kx, and this is called scalar multiplication. For all vectors x and y and all real numbers r, s, and t scalars, we have the following. The vectors x and y, real numbers, scalars r, s, and t. If you multiply a vector x by 1, it stays the same. If you multiply a vector x by 2 scalars this way, you could do the multiplication of t first, then multiply by s. Those are just properties that I'm sure that you could agree on and follow. R times x plus r times y, you could do that. And you could do s times x and t times x. Or of course you could add s and t first, whatever works. Third page, this is the second page. Let's go to the third page. Third page is the following. We begin by considering vectors in the plane. Recall that r to the second denotes the set of ordered pairs of real numbers. So that's what we have. Just to remind you about vectors and components, those are called components x and y. So if you have a vector called x1, y1 as a vector, that's why we use the letter v, and a different vector is called w. Of course, you could call this one v1 and this one v2. These are two vectors. Adding vectors, we add the components. So x1 gets added to x2, and y1 gets to be added to y2. And this is how you multiply scalars. You multiply the components, each one by a scalar. So if you have a vector xy, geometrically this looks like you go x on the x-axis, x amount, and you go on the y-axis, y amount, and you reach the point. As you can see, it's a vector starting at the origin, pointing to the xy location, identifying vectors in r to the second with geometric vectors in the plane. So we're done with page 3. As you can see, I'm trying to make it a short video. There's no need to make it lengthy. As much as we can, we'll do our best. So if the vectors are not like just like basically x, I, like the previous page, and 0, y, you could have a vector v going to x1, y1. You could have a vector w going to x2, y2, wherever that x2, y2 is. The sum will be the diagonal of the parallelogram that you could form, as you could see. That's x1 plus x2, y1 plus y2. This is for later on if you multiply by scalar. If you want to multiply v1 by scalar and keep w2 as is, you're going to end up going all the way up to here. That's a new vector. That's for the introduction when I mentioned we have a linear combination of two vectors. So that's linear combination is going to form all solutions, and that's why we call it the general solution. Also, we could write the vector v, which is xi plus yj, this way: x times 1, 0, and y times 0, 1, where I is one component on the x-axis, nothing on the y-axis, where j is one component on the y-axis and nothing on the x-axis. These are called unit vectors. This would be the 0 vector, as you could see right there. As you can see, this 0 is bold, and this is the regular font right here for the components. This would be the additive inverse for any vector x, y. So we're done with page 4. Let's go to page 5. Page 5, if you move on to r to the third, you're going to have the components x, y, z. That's pretty much it. And that's a vector v that has x component and y component. So they meet right there in the xy plane. And you go high up to the z component. So you're going to reach somewhere here. If this is positive, 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 as you could see, we're in the first octant pointing to it from the origin. Those are basic ideas. How do you add vectors in 3 dimensions? How do you multiply a vector by a scalar in 3 dimensions? Pretty much the same thing. This is page 5 or 6. We're almost done. There is nothing left on page 6. We're just writing the vector in the components of I, j, and k, and mentioning the 0 vector in the 3 dimension. And how would you add vectors in 3 dimensions or more? And how do you multiply a vector by a scalar if it's in n dimension, not just like 2 or 3. I think that should do it for 4.1. And as I mentioned, it's good enough. I don't want to write anything. There is no need. And we're going to make it quick. It's about 8 minutes, 14 seconds. Thank you.